Okay, thank you. Well, for people online that couldn't hear, the important thing you missed is that supermassive black holes are important, and I'm sure you all know why. And I'm gonna be talking about AGN TDs because that's the way we can probe them observationally in the EM spectrum. That being said, now we're talking about AGN. AGN are super important. Obviously, they're the central region of galaxies that emit a non-stellar emission with broad lines. And the current status of the field is that in the center we have a supermassive black hole. Around it we have an accretion disk, which is how the energy is liberated. But the whole thing is a mess, right? Like we also have an X-ray corona is the source where X-rays come from because the accretion disk cannot produce X-rays. We have clouds around to produce broad lines. We need different clouds to produce narrow lines. We have a system that absorbs our central source that we call torus, and have no clue what this is, etc., etc. So everything is a bit of a mess, but this is a very simplified picture. And one of the problems why everything is a mess and we cannot understand better is because AGN are very small, right? Like they're in the center of galaxies, typically much less than 1 parsec, and the galaxies are, megaparsecs away. So we cannot resolve them. So we cannot try and study different regions. So people have tried to come up with ideas how we can improve our knowledge. And one particularly successful technique is reverberation mapping. So what this technique does is uses the fact that AGN are variable in different wavebands, and different wavebands come from different regions. So if you study the variability of two wavebands, in principle, you study the physical connection between these two physical structures. The typical way that reverberation mapping started is to study the broadline region, which is the broadline region is photoionized by the central source. This photoionization is going to produce the broad lines. And if you study the variability of the central source in UV and optical up here, you do the broad line variability too. You see the two are correlated. The broad line is a bit less variable and shifted in time, which is what you expect. You can even do some cross correlation, study the whole system in detail. And actually, that's the best way we have to constrain the black hole mass. Okay, why I'm saying all that? I'm saying all that because another interesting thing you can do with reverberation mapping is to study the inner source. If the X-rays are illuminating your disk, then you can study the variability between the X-rays and the disk emission, and then you can constrain the connection between the two. And that's what I'm doing. So that's called disk thermal reverberation. Obviously, if you have X-rays come from a cellular region, you do expect some of it to be reprocessed in the disk, right? So you do expect to see something there, some features. Now, why this is important? Again, we can study the connection between the two systems. And what this means in practice is, one, you can try to constrain the radial profile of the disk temperature, which is a direct, it comes directly from the theory, but there's no way to prove it otherwise because the spectrum that could be done is very agnostic to that in the end. So that's one very important thing we can test. And also, if we find a good way to probe this connection in a physical model, then we can use this physical model to constrain in the regions that we have no hope to resolve anytime soon. Okay, that's not news. People knew about that. What changed is that around 10 years now ago, people went and used Swift and a lot of ground-based instruments, and even HST in this case, and observed different AGN. And this is the first example that I have this kind of intense monitoring. You see light curves that span several months, observed twice per day. That's an amazing light curve. You can actually do all the kind of variability studies you want to do. And what they want to test is exactly that. Try to correlate UV and optical light curves and see if we can say anything about the temperature profile, etc. And you can see already by eye, okay, the variability is there, you can see it, but also if you try to go from top to bottom, you can see that, the peak, for example, in the top is a bit shifted on the right and the bottom, which is exactly what you expect. You expect to be a delay, and the top is more variable than the bottom, etc., etc. Top and bottom is blue and red wave paths. But obviously, people do that more properly. They don't look just at light curves, they do a cross correlation. And when you do that, you can estimate the time lags. They did all of this. And what they found is the time lags are increasing with wavelength, with a power law to the 4/3 in the index. And that's very important because that's exactly the power law you expect for the temperature. That power law is predicted directly from this radial profile of the temperature. So this study kind of is the first evidence that observation we have to prove that actually the temperature profile is what we expect from the typical accretion theory. But also a problem arose at the time, which was that the absolute values of the lags are a bit larger than naively expected. So there were different things there. People came up with a lot of ideas why this might be the case. But my favorite, and the one that I want to talk about, is what Elias Camus, Joseph, and collaborators did, which is they went back to the system and tried to actually study the response instead of using simple approximated scaling relations. And what they did is, you define your black hole. Okay, we don't care about the black hole, but you define the accretion disk and an X-ray source on the spin axis of the black hole. You illuminate the disk, and you wait to see what happens. Now that sounds simple. It's not simple. It's very complicated. You have to do the GR ray tracing. You have to estimate how much energy is coming to each small bin of R and phi in the disk, etc., etc. But they did it. They're good scientists. They did it. So once you do that, you can estimate the time lags. They estimate the time lags for different physical parameters. They compare their model with observations, and there is a perfect agreement. A perfect agreement for typical, accretion rate and height of the X-ray source.
So can you explain what do we see in this cartoon?
So here you have again supposedly an AGN, right? You have a black hole, an accretion disk. Okay, it should be two sides, but not just focusing. And this is the X-ray source. So what happens is that your X-ray source illuminates the disk, and the disk is going to absorb some of it. It's going to reflect and scatter part of it, right, due to its albedo in different processes. But part of it is going to be absorbed. The one that is absorbed is going to increase its temperature. And then the emission from the disk is modified because of this excess energy that you give it. And then, yes, so the excess emission you get over time is something like that, on top of the typical disk emission you would have otherwise. And then you can use this kind of response, which is like, if it is a delta function illumination, then it's a green function, basically. That's the thing. And you can use that to predict time lags. And that's what they did. So this model, works well with the data. And it was, that was kind of the current of the then state of the field when I decided to enter the field. And what I want to do was a bit something different. So what I want to do was take the light curves and see if we can reproduce the UV and optical light curve, or in particular the variability for the X-ray variability we see. Because people had focused too much on the time lags, and I think there's extra information on the variability that we see. And I decided to do that in the Fourier space. Now, why the Fourier space? There are several reasons. One is it's much easier to handle. When you have done your work, it takes a lot of work, but it's easier to handle, and it's easier to interpret, okay? So if you have a power spectrum, which here I denote by P, you see that it's directly connected to the variability amplitude. So once you have a power spectrum, you can study the variability in different temporal frequencies. And what you see here is that the connection between different power spectra is just a multiplication, much easier than convolution, etc. Like time domain is a bit messy. Okay, obviously I was not the first one who knew that, right? That's old theories. Why I chose to do that and people haven't done it before is because now it was the first time that we had the data to do that, right? You need a lot of data to sample a lot of frequencies, very good cadence, like, the process is difficult, but it was the first time that we did have that in optical data. So I decided to try. And what I did is, well, I use the same model as before, where I estimate the response and try to build a model to predict power spectra of the UV and optical given an X-ray power spectrum. And that's supposed to tell you how I did the model. It's just the transfer function in Fourier space is just the Fourier transform of the response. That's not important. The physics is, again, you illuminate a disk, you predict what happens to the Fourier space, which gives you amplitude per frequency. Once I did that, you can start making predictions, okay? So you can start making predictions like what happens when we change the accretion rate. You see less variability when the accretion rate is higher, which is here. And that's because the amount of energy you deposit to the disk is smaller as a fraction to the emission that you see at the end. At the same time, you see that the disk is more variable in the blue wavebands instead of the red wavebands, just because of the distance from each emission region. Okay, these model predictions are not that important. Obviously, these are things people have claimed to see before in other observational data, so they were interesting to, at least as a check that we're consistent with that. But when you have a model, that's not very interesting, right? You should try and test your model with data, and that's what I did. So we have an X-ray power spectrum and then different UV and optical power spectra, and I fitted all of them with my model, and I was able to find a very good fit. So that was, a first surprise. While I was developing the model, I was not expecting a very good fit, to be honest. So I was already thinking why and how I'm going to explain that. But here there is nothing, like there's no cross normalization, there's no freedom. You have defined the geometry, you have put the source at specific region, and then you let it do its thing. And it's working, which was crazy. Now, when I saw that it's working, I realized that we can do an extra thing, which is, my model is based on the model that Kamun developed. So we can fit the time lags simultaneously with the same self-consistent fit. And it's all working. Now we can get the absolute value and the shape of the lags in a fit that at the same time explains the variability amplitude in different frequency ranges and different wavebands, in a consistent way. So, I was very happy at the time. My main result is that discrete processing can explain the whole variability properties of AGN. We were able to constrain some parameters of the system. The one I'm usually more surprised about is that we were able to constrain the host galaxy reddening, which doesn't make sense why, but the variability is affected in different bands differently. So we could do that and compare it to narrow line ratios from the host galaxy and see that we're actually consistent, which was probably the biggest surprise in this for me. So okay, this was a paper a couple of years ago. Since then, I've done a lot of things. I've been working a sample. I've tried to evolve the model, etc. But now I want to change gears and talk about something that I've been spending too much of my time lately, honestly. So I will stop here, and I think it's a good time. If you have any urgent question about AGN or any of this science, otherwise I will continue, and you can ask me then. But yeah.
How do you calculate the response function? I mean, you just assume that the accretion disk extends from the X-ray emitting region all the way up to the optical emitting region as a stub. What is the assumption here?
The assumption is the Rin, the inner radius, is equal to the ISCO, the innermost stable circular orbit. It depends on the spin. And the outer was 10,000 Rg.
Okay.
So, well, to be honest, if you go much beyond that, doesn't affect, because of the incident angle and how much and the wavebands that emit that far, you don't get that much of a difference. And then the computation is scaling because you don't have
and you take into account all the light bending and so on.
Yes, yeah. That's all work that Michal Dovchak has done. Yeah.
Okay.
So they do it. Anything else? Otherwise, I'm going to check.
If you take the disk, the thin Shapiro-Pillai disk or whatever, to go all the way to the ISCO, you don't have the so-called hot inner flow
Yes.
from which we get the corona. So do you assume then that you have a small corona? You actually put the corona up there, which is a mathematical tool, but the physical picture is different. You need self-consistently to have that field.
Yeah. So okay, that was the first study when people were saying that this model doesn't work at all because they saw that the lags are not working. So I was trying to just prove them. If you do your things zero order approximators, but at least with some physics in it, it works. You're right. There are a lot of more details that go into that. The most recent, or at least the paper I was working on now, and we try to have that, is what Yossi was doing, which is you take some part of the inner accretion disk and you deposit, you assume it's there, but it's cold, and all its energy goes to the corona. So that's how you thermalize it. Or you can assume that it's somehow externally thermalized with some kind of spin process from the black hole. There is no, the disk is always thin. It's always an open or saturation thin disk. We don't touch the disk there. The problem is, one, gets complicated. Two, doesn't seem to be needed by the data we have right now. Doesn't mean, obviously these are going to change if we change the geometry and everything, but the fact that it doesn't need it yet means we don't have the data to start pushing that much. Then about the X-ray source, indeed, it's just a mathematical tool. It is a good approximation when you have a spherical thing, but doing anything more complicated, it really, starts to mess with your GR tracing, etc. Or at least that's my understanding. I didn't decide to do that. That's why we do that. Yeah, definitely we need to do something more advanced, and I agree with you.
This end of there is in what units?
Electron, sorry.
So it's 4 times electron?
No, 4%.
Ah, okay.
4%.
I thought the percent was in the error. 2%
No,
okay.
sorry. No, it's around 4%.
Okay.
4 times second to 548. That's very good thing. Like, what are you doing?
Also, the structure of the equation, this should be.
Yeah. Definitely.
Okay.
Yeah, sorry, it's not well. Okay, anything else? Otherwise, I'm just gonna change the topics. Yeah, I'm gonna change topics. So now I'm gonna talk about TDs. And TDs, okay, forget everything you heard about AGN and assume you have a normal galaxy, right? What happens in a normal galaxy is just you have a black hole in the center that does nothing. It just stays there. It can affect the rotation of the stars, etc. Our own galaxy does that, but that's it. It doesn't do anything else. So if you have a star coming too close to the black hole that is just there, if the star goes closer to the black hole than the tidal radius, which is where the tidal forces of the black hole overcome the self-gravity of the star. What's going to happen is the star is going to be stripped apart. Part of it is going to be accreted onto the black hole, and this accretion again is going to emit a flare over the whole electromagnetic spectrum. And in terms of how it looks in time, this is going to be what you see, right? You start with 0, very quickly you reach a peak within a few days or weeks, and then you start decaying with a power law to the -5/3. So TDs are very interesting because one, they give us an option to study supermassive black holes that do not have an accretion disk like AGN, right? And these are 90% of the supermassive black hole in the universe. So if you want to understand black holes, that's a good thing to do. And two, something very interesting, when you study AGN, they're valuable and everything, but at the end of the day, they're more of a steady state accretion. TDs let you study the whole accretion process within timescales that we live, right? So you have the formation of the accretion disk, the accretion of the matter to grow the black hole, and the depletion of the accretion disk. And you might even have the launch of the jet, and then the jet disappears, etc., etc. So if you actually care about accretion physics, that's an amazing system to study. Now, the fun thing about TDs is that they were first predicted theoretically and then found. You see the papers here from the 80s. The first time we found them is in the 90s with ROSAT, an old X-ray emission for people who are not familiar. And that's because people thought you're going to find TDs mostly in X-rays, right? Because if you do the math, you find that the typical peak of the spectrum is going to be in soft X-rays. Well, here's the histogram of the TDs that we knew up to 3-4 years ago. And you see that indeed, in the 90s, we found a few with ROSAT. Going on, we found a few with XMM and then with Galax in the UV. But what really changed the field is this wide field surveys like ZTF, etc., that they scan part of the sky every day, a very large fraction, that large that you can scan the whole sky every 3-4 days. And as you start doing that, you build a baseline, you can go and look for transients and you detect TDs. And that's why you have this huge peak in the histogram. And right now we're at the phase where we detect 20 or 30 TDs per year. One thing to notice, there is no infrared there, and that's what I'm going to be talking about, and I'll tell you in a bit why. Now, if you wonder how it looks in ZTF light curves, that's all ZTF, which means optical, right? Around 5,000 angstrom or so. What happens is you have, again, nothing goes up a few days, then star goes down. It's a bit of a zoo. It's not as clean as the theory would like, right? But at the end of the day, we're kind of confident that these are TDs, and we can explain the whole system is a bit complicated, so it makes sense that it's not as clean as we thought. Now, there are a lot of problems with TDs, and I don't have time to talk about all of them, but I want to focus on one. So one thing that people noticed early on, as soon as they had a couple tens of them, is that TDs are found in rare galaxies. So that's what I'm showing here. Let's focus on the left first part. So the left, you see in the y-axis is the UR color of the host galaxy, and the x-axis is the stellar mass of the galaxy. And if you see the contours on the back, the gray is from the all SDSS sampling in the nearby universe. And what you see is you have a lot of galaxies down here, which are blue and not that massive. These are typical star-forming galaxies and spiral. And then you go up there, which are more red and more massive. This is where you typically find your quiescent galaxies. And then in the between, going from blue to red, we have what we call green valley. And you see like the contours, maybe you don't see very well, but there are not many there. They're supposed to be a minority among the galaxy population. But somehow, when you will do this analysis for hot galaxy TDs, many TDs, many times more abundant than we would expect typically, are found in this green valley. The same is true for X-ray TDs, right? These are the samples from Rosita that came out a few years ago, and they find the same exact problem. Another way to look at the same problem is to see this kind of plot, which now you see H alpha equivalent width in emission over H delta in absorption. And you see again, the black points are the SDSS, you see where the most of them are. And now you have your post-starburst or kind of green valley galaxies lying somewhere here. It's very, not that well abundant in terms of black points, but then you put the TD host galaxies there and many of them are again there. So that's another way to see this thing. And that's a problem. And that's a problem because it means if it's true, there is a way in specific galaxies, in very rare galaxies, to boost the TD rate in comparison to other galaxies. But that's not the only explanation. Another explanation that came out is that this might be an artificial effect of observations because the TDs that you would expect to find in star-forming galaxies are going to be obscured. And if they're obscured, you don't detect them in optical, all right? So that was kind of the motivation of our work. And we decided to study the infrared TDs. How did we do that? We used WISE. WISE stands for Wide Field Infrared Survey Explorer. It was a NASA mission launched in 2009. It had 4 filters initially. After a couple of years, 2 of them couldn't work anymore. So it had 2, W1, W2, around 3.4 and 4.6 microns. So completely the mid-infrared. The nice thing with WISE is it scans the whole sky every 6 months. Okay, it has a specific polar orbit that can scan the whole sky every 6 months. So you can get light curves of the same galaxy every 6 months in the mid-infrared. If you detect something goes off, you can say, oh, there's something interesting there. Let's go and look at that. And that's what Kishele did. I did none of it, right? Kishele is the expert in this. So what he did, Kishele there is a postdoc at MIT, and he's going, actually in a few weeks, going to be a faculty in Columbia. What he did is he ran image differencing for all the WISE archive. Well, I guess the guy was boring at some day. So the way you do that is you take the reference, which we use the first 2 years as a reference image. You take the new image you have a couple of years later, you subtract the 2. If there is any excess on the subtraction, then you call that a transit. If there is nothing within statistical errors, there is just an upper limit. So he did that for the whole sky, the whole archive. He found millions of transients. Obviously, most of them are going to be galactic transients. A lot of them are asteroids, right? But there are a lot in extragalactic sky. So Kishele doesn't like the extragalactic sky. So what happened is he came to my office. He showed me this light curve, and he told me, what is that? I had no idea. Well, he had some ideas, but he didn't want to do it. So the first question we had to ask is, how do we decide what this is? Well, obviously, we know when the sky is, right? So we can get an optical spectrum, an optical image, which is what you see here. That's a nearby galaxy. We can tell it's in the center, it's a nuclear transit within 2 arc cycles. So the moment we decide it's a nuclear transit, you don't have a lot of options, okay? It can be an HN, a supernova, or a TD. There are not much more that we know from optical or X-ray surveys. And this is its light curve, right, in difference flux. So you have upper limits just because there's no transit in the beginning. Suddenly it goes up quickly and then goes down. At this point, are 6-month cadence, right? So what we did, I'm going to speed up a bit. The way we want to go for that, it was impossible for us to decide if it's TD based on spectra, because when we found that, we're already 7 years after the peak, right? There is no hope to do any spectroscopy to tell you what is there. But we can exclude everything else. So we start by excluding AGN. That was easy. There was no X-rays. There was no broad lines. You put the narrow lines in a BBT diagram. It's a star-forming galaxy. It's not an AGN. So we kind of said, cannot be something driven by an AGN. It was very easy to exclude supernova, because if you add all these flux, you go to something that is kind of 5, 10 to the 51 ergs radiated energy. For people who do supernova, that's impossible. That's no way to do a supernova do that. You can do a super supernova, that's another mystery. So we decided, it's not the one, it's not the other, it has to be a TD. Now, why is this interesting? Well, it's interesting because this galaxy lies at 42 megaparsec, and if that's a TD, then this is the closest TD we've detected during the time that we have, wide field service. And for us, that meant a lot. It meant that, we did that, we didn't know what it is, we tried to look up, but then we realized we just did that, one exercise, and we found the closest TD. It means there are a lot of TDs in the infrared that people don't see in the optical. Because if you look how the optical looks for this TD, it's nothing. It's all upper limits. There is no optical detection. We did have WISE, Assassin at the time that would look at the same part of the sky. We had Panstar a few years before. We also checked Catalina. We checked all the sets we can get our hands on. Optical did nothing. It was a flat thing. So, the closest means there are a lot of them. No optical means there are a lot of them that optical people miss. So why is that interesting? Well, coming back to the QR versus MGAL color plot, you see again the green valley, et cetera, et cetera. Our galaxy lies here, which is a completely different region where all the other TDs is found. So we thought, we found a lot of TDs that people cannot find, and also we find TDs that probably are different in different environments than what other people find, okay? So that was kind of what we did in this first work, and then we had a very enthusiastic student, Megan Masterson, a grad student at MIT, come in and help us do a sample paper. So, and by help us, I mean, she did all the work, right? She was leading the whole thing. So in this sample paper, we focused only within 200 megaparsec, because it's impossible to do the whole sky randomly. It takes too much work. And we thought, let's look what is within the 200 megaparsec based on a galaxy catalog that we knew. And we found 18 TD candidates. 12 of them were very sure that it is. There was no other indication. The other 6, there were some very slight indication that might be something else. So we decided to cut the group in 2, like gold and silver. So you can see the light curves. Few things to highlight from her work is she was able to estimate the luminosity function. So what you see here is the luminosity function from Megan, from the mid-infrared TDs, and then you have the optical in the orange and the X-rays with green. And you see that mid-infrared TDs in the local universe are at least as abundant as optical and X-ray, okay? And actually the mid-infrared are lower limits because we have excluded a lot of sources that are faint. So we expect that this would go even higher up in our case. Then going back on the overabundance in rare galaxies, we don't find that in infrared, which is exactly what the theory predicted, that if you do the same exercise in infrared, you're gonna find all these dust obscured TDs that people in optical cannot find, and you're gonna explain why this overabundance happens. So again, this is the same plot that you saw before. Now what is that, maroon or, yeah. These points are the mid-different TDs. And you see none of them is not even close to where these weird galaxies are. So let me see what I have next. Okay. So, that's what we did. We put that out almost a year ago, it was done. It was published, so we're very happy. We kind of, explained what people predict before, but also found that the whole WISE archive is crazy. It has so many things in it that no one has looked before when it comes to extragalactic astrophysics. So we decided to, have a deeper look, and we realized we kind of found something very interesting. So we started working on that. We spent the last year and a half working on that. So I don't have time to talk about all of it, but just a few highlights that I think are very interesting, are more excited for me. One is we got James Webb spectra for some of them. And here is one example. That's the TD that we first found in 7392. You can see it in red. In black, you can see a nearby AGN, 7469. And what is interesting to notice is that both of them have high excitation lines that I denote with pink, I think, like neon 5, etc. And this directly tells us that, the TD that we thought is a TD has some accretion event in it. There's no other way to produce these lines. They're very high ionization, like more than oxygen 3, etc. The other thing you can notice is that the TD spectrum is different to the AGN spectrum. The TD host nuclear spectrum, right? So we have this huge bump around 10 and another bump around 18. These are silicate features. Typical AGN don't show this kind of emission. They have either a bit slide of emission, like what you see here, or they have huge dip because of absorption, especially ultra-luminous infrared galaxies. For people who are familiar, they have a huge dip. So we're trying to make sense out of this. We've been working on that for a while. What we think, our current working theory is that now the central source is off, and we're probing echoes from distant material, and this distant material is more optically thin. And because it's more optically thin, we can get a lot of emission in silicate grains. We're still working on that. There's a few things that we need to figure out, but it seems to be consistent with modeling when we use, dusty and these kind of things. But in any case, that was the first time we got the TD spectrum with James Webb. It's, for people who haven't used James Webb, it's unbelievable. Like coming from X-rays, I couldn't believe it. The spatial resolution, the energy resolution is like mind-blowing, which also puts a lot of problems because you have so many data, you have to do something with that. But it's unbelievable. You can do so many things. We're working to make sense out of it. There should be a paper coming out within the next few months to just highlight a few things, but there are a lot you can do. You can study, the PAHs in different parts. You can study the warm molecular gas, which is what I'm going to do in this, in TDs, hot galaxies versus AGN galaxies, etc., etc. But then in the last 2 minutes, I just want to say one thing I did recently, and I really like it, which is connection between TDs and neutrinos. So for people who haven't heard before, there are a couple of claims in the literature that they found neutrino events as, as reported from IceCube, to be coincident with TDs. These were, kind of a sample paper for 3 of them. We have 2 more recently, Carl Belzer and Young, 2 different groups working. The very interesting thing to notice is that in all cases, the neutrino arrival time is coincident with or very close to the peak time of infrared, which kind of sparked a lot of ideas of how can you do that. Like,
where is the neutrino here?
It's the vertical line. Sorry, I should have said that. Do you see the vertical line?
So they see one neutrino coming?
Yes.
One.
Yes. So you get one alert from IceCube, which IceCube tells you, let's say in this case, I think is the case, I'm not sure, actually, I have to check, that is 50% probability to be astrophysical or more. It gives you energy, and it gives you the area of the sky that comes with a specific.
This is days after the event.
No, that's like hundreds.
Yes.
Yes.
That's okay for them.
Yes.
There is a big discussion.
But I will explain, right? So their initial analysis goes everything within a year. And it kind of makes sense because you don't know what triggers the optical TD emission, right? It's not necessarily the accretion disk. It might be something else. So then the way you accelerate neutrinos might not be the same that you emit optical. So if you take time, because for example, the radio emission is delayed in TDs, right? Which might say, we have some delay in how you accelerate particles. So it's not as crazy as it seems in first glance. But the interesting thing is it aligns with the peak in the infrared, which gave them the idea, yes, which doesn't make sense, right? Which gave them the idea that there might be something there. What they did is they collected a lot of accretion flares, they call it. So flares come from the nucleus of galaxies. They put them in a plot of infrared flux versus infrared strength. By infrared strength, they mean how big the flux is with comparison to the baseline variability. And they find that the three TD candidate, the three accretion flare galaxies with neutrino coincidence are the blue field points there, which are on the top right part of the plot. So what Short and collaborators did back then, they said, okay, if that's the case, they assume a prior, the infrared flux and neutrino flux correlate. And if that's the case, they prove that these three detections are more than 4 sigma detection to indicate that there's a strong.
These three things are worse.
Well, if you get the whole sample and you assume the neutrino flux correlates with infrared flux, you do some bias analysis that they want to do, and then you get that this means that more than 4 sigma, there is a connection between TDs and neutrinos. Well, I didn't like that, right? So what we did the same analysis, but now we focused on mean different, because if that's actually true, we find TDs in infrared, which means we're going to be blasting this scaling, and we can find all the neutrinos we want. So actually, when we started, I was excited. Oh, maybe there are neutrinos to find. So I put a student, she's an undergrad student at MIT, second year now, to do the analysis. She again focused on the nearby universe because that's where the brightest things are. And she found all the accretion flares in the WISE archive and tried to connect them to neutrinos. So this is the sky map that you get from neutrino, the gold with the error bars. And the blue is our accretion flares, okay? You can see there are 3 coincidences spatially. There is 0 coincidence temporally. They're apart by like 5 years or something, which doesn't make sense. Not only that, we can put our accretion flares on the same plot, and our flares now are in red. The coincidences with neutrino are now in green. Sorry for the change in color. So we completely prove that there is no connection between infrared flux and neutrinos. Once you prove the prior wrong, you prove, I guess, the conclusion wrong. So we say that there's nothing. Megan is now writing a paper, try to put it out as a short letter because everyone has been citing the other paper that. And again, I want to be diplomatic, and I will say maybe they're different TD population. I don't know, but we just say this is not the case for us, and infrared flux does not correlate with neutrino flux. That's it. Yeah. So I think I will stop here, and thank you for your attention.
Question.
I was wondering about the association of TDs with green valley galaxies in the orbital or in the X-ray. Would this have to do with a contrast in the sense that star-forming galaxies have a lot of optical in the nuclear region, so it would be harder to find something, a blip that goes off. And the same happens in early type galaxies that have very strong voltages, they are very bright in the orbital. So again, it would be hard to detect a blip because the background is very strong. Now, on the other hand, in the mid-infrared, okay, in star-forming galaxies, it can be an issue if you have a very strong transformation because you have the PAH emission. But in the galaxies that you showed, for example, this has the bulge looking at the image. So in the mid-infrared, the bulge is suppressed. because you have the old stellar populations. So this could increase your contrast. And in the mid-different, you have a better chance of finding TDEs in all the stellar environments than you have in the optical. So would that make sense? Or, as you mentioned, is an obscuration effect? I mean, have you measured the obscuration? You know that it's obscuration, or it could be something else?
Well, thanks for the question. Now we're in a field I have no idea what's going on. So I will try to answer your question, but I think if it is a contrast effect, I was talking to people from optical, and they told me, they have tried different things and they cannot explain it with a selection effect. Even if, if you ask, because I think what they did is, assume that the flux of the TD in one galaxy is equal to the flux of the other galaxy, right? And then it's not about contrast anymore. And they say
it is about contrast, because if the flux is the same.
No, yeah, that's what I'm saying.
Your background.
That they said if it was the same flux, that's what I remember talking to them, they should have detected in other galaxies. They should have this, because the overabundance is like a factor of 5 or something. It's not just, a few percent. Now, when it comes to mid-infrared, I do think we see a lot of obscuration, and we kind of saw that from the Balmer decrement, for example, or also from James Webb. We kind of see that there's a lot of dust there, but I'm not I cannot say that this is. I hadn't thought about this bulge explanation, so I cannot say that dust is the dominant. The reason we think dust is important is it was coming from the lack of optical flare. Which is, like in one galaxy, like here. Okay, now that it's in Zamsky, so it's not the best, but you can tell, it's a factor of 100 in difference imaging, which, it's 40 megaparsec. If it was any kind of typical TD at 40 megaparsec, Assassin should have found it, regardless of the. So that's why we went with dust. But that's a good idea, so I will start thinking about it. But Balmer decrement is definitely there, so we know that there is an absorption effect. We don't know if it is dominant, but we know it's.
Can you measure how much the extinction gave?
We did, but I don't remember the. We did we do now with James Webb, and I remember that because we do that now. And AV from James Webb, which comes from modeling, so it's not very accurate, right? But it's a few. It's like 4 or 5.
Magnitude.
Yeah.
Oh wow, okay.
Yeah, it's above 1 for sure. It's like, and that's ages after, like 10 years later with James Webb, which includes modeling. When I said that we see optically thin dust in infrared, I meant optically thin in the mid-infrared. It's not self-absorbing its own emission. It's in the optical, is still optically thick by far.
Any other questions? Everything was understood fully. Right, okay, good. So in this case, have a wonderful Christmas and a great time during the festive period. And with this, we finish this semester, right? Okay, the talks for this semester, and we will reconvene, I don't know, in January for the talks. All right, okay, guys, so have a great time, right? And let's thank the speaker once more.